Okay, so far this unit we have looked at several different types of substances. We have looked at ionic substances that are held together by those electrostatic forces. We have looked at metallic substances that are held together by the metallic bonding, the sea of electrons. And we have looked at molecular substances, the covalent bonding where we have individual molecules. So the last type of substance we're looking at is known by a couple different names. In some cases, it's called covalent network solids. In other cases, they're called macromolecular. And if you think about the meaning of the word macromolecular, macro meaning big, it's like one big, huge molecule. So you can think of macromolecular solids or covalent network solids as one big, huge network of just all covalent bonds. Just one thing covalently bonded to another covalent thing. Now, how is this different than molecular substances where we do have covalent bonds? Well, if we look at this picture here, on the left, we have a typical molecular solid. Here is one molecule. Here is another molecule. There is a covalent bond between this atom and that atom. Okay, there is a covalent bond here. Here's another molecule. There are covalent bonds within. So the intramolecular forces are covalent bonds, and those are very strong. But if we look, what's holding this together? Now, if you look at both of these, they kind of both look similar. I see kind of a lattice structure here. They both look like they're crystalline. However, in the molecular solids, we want to focus on the attraction between one molecule and the other molecule. What is holding these two together? Well, this is not a covalent bond. This is an intermolecular force. It might be dispersion forces or dipole to dipole or even hydrogen bonding, depending on what kind of molecule we have here. But the point is to see that a molecular solid is made up of individual discrete molecules, which are all held together very strongly, but the force between molecules from one molecule to the other is that intermolecular force. So these intermolecular forces are very weak. So we have all these weak points here, and it's fairly easy to overcome these forces and to melt it or change it into a gas, to boil it. So we have weak and strong. Whereas when we compare this to a network solid or a macromolecular solid, notice that this is just a whole bunch of atoms, and these are all covalent bonds. Notice no matter where I go, no matter what I look at here, every one of these bonds is covalent. And remember, covalent bonds are very strong. So there are no weak points at all in this whole structure. So in order to break up this crystal, in order to melt it, I have to actually overcome these covalent bonds. So that's the difference between molecular solids made up of individual discrete molecules with those weak intermolecular forces holding them together, and a network solid where it's just all one big huge network of those very, very strong covalents. Now, because of that, we see very different properties for things that are molecular solids. First of all, again, the macromolecular, the substance is just, you can think of it as one big, huge molecule. There are no individual molecules, just a big, giant molecule. And since there are no weak points anywhere in there, it is a very, very strong substance. It is all held together by those strong covalent bonds. So that means we'd expect these guys to have really, really high melting points. Okay, again, to melt it, you've got to overcome those strong covalent bonds. Also, since the electrons in here are in a covalent bond, they're localized. This is very different than the sea of electrons that we saw in metallic bonding. Okay, here they're localized, so they do not conduct electricity. The heat thing, that depends on the substance itself, but at least primarily electricity, we see these guys do not conduct. And also, because they're all in this rigid kind of covalent bonding, they tend to be brittle. There's not a lot of give or take here. So to see some examples, I'm going to take you to my buddy Hank. Take it away, Hank.
The diamond in this ring will cut into any substance on Earth. It's the hardest natural material on the planet. But it's just carbon, the same element that makes up the graphite in this pencil lead, which is so soft that its intended purpose is to rub off on stuff. The atoms are of the same element and they're all bonded together with covalent bonds, so what's the difference? Well, their atoms are arranged differently. They form different atomic networks and therefore different network solids. Network solids are one of the three types of atomic solids we've talked about, materials that are made of individual atoms rather than molecules or ions. The cool and special thing about network solids is that the atoms exist in, you guessed it, a networked structure. That is, each atom is linked to several others in various directions. Like all networks, this arrangement makes the structure both strong and stable. It also provides some other properties that may surprise you. If you've seen our episode on atomic orbitals, you know that the way the electrons in a chemical bond orient themselves, that is, the way the orbitals hybridize, has a big effect on the properties of a substance. If water's orbitals hybridize differently, for example, it might not be polar, and life as we know it wouldn't be possible. It's the same with network solids. Orbitals and their hybridizations make a huge difference. Thankfully, though, orbitals can't be different. They are the way they are because of the laws of physics. So first, let's look at carbon. Pure carbon can bond with itself in two different ways. In the first scenario, the outer electrons of each atom are arranged into sp2 hybridized orbitals with two other atoms for a total of 3 lobes in a flat trigonal arrangement. This creates a sheet with a hexagonal structure and with one unhybridized p orbital left on each atom. These orbitals form pi bonds that merge into an extensive network on their own, and this gives the structure its real strength. You know this carbon network by its street name, graphite. The pi bonds within each sheet are really strong, which allows graphite to withstand a lot of pressure, but, as with any sheet-like formation, only in 2 dimensions. The sheets are only held to other sheets with really weak van der Waals forces. They allow the sheets to slide on top of each other so they can easily be removed layer by layer. That's why graphite is so fantastic for writing with. When you use a pencil, layer after layer of graphite is being transferred to the paper. That slipping sheet structure also makes graphite an excellent lubricant. It can break down into an extremely fine powder of slippery platelets that almost any substance can slide easily over, which is why it's great for things like sticky locks. And because the electrons that form the pi bonds in the graphite are able to move from one atom to another, graphite also conducts electricity. But most of these properties of graphite, you'll notice, don't apply to the other type of network that carbon can form, diamond. Even though the graphite in a pencil is made of the exact same thing as diamond, pure carbon atoms, they're different from each other in almost every possible way. And all of these differences are simply because of the way their atoms are bonded. In diamond, the bonding electrons in each atom are arranged in sp3 orbitals, 4 lobes that are as far away from each other as possible. Again, information you should have in you from the orbital episode. Each lobe in that tetrahedral structure overlaps and bonds with one on an adjacent carbon atom, creating a totally uniform 3-dimensional network of carbon in every direction. So any stress on this network will be resisted by multiple atoms and multiple bonds. This stability is what makes diamonds so famously incredibly hard. But the downside is that this rigid structure also makes them quite brittle. In other words, they break before they bend. And like any crystalline solid, they tend to break along the seam between atoms, called a cleavage plane. And these are the places that the diamond cutters attack first. And here's another way that the diamond's network structure makes it totally different from graphite. Diamonds are electrical insulators, not conductors. This is because the carbon atoms in diamonds share sigma bonds, not pi bonds, which doesn't allow the electrons much freedom of movement. And if an electron can't move around, it can't be used to transfer energy in the form of electricity or anything else. But even though diamond is terrible at conducting electricity, both graphite and diamond are good conductors of heat. That's because of the strength of their covalent bonds. These tight bonds require that when one atom vibrates, all the atoms around it vibrate in exactly the same way. So when thermal energy increases in one region, it spreads quickly throughout the diamond or graphite. Even though there is some space between the sheets of graphite, the structure of the sheets is so rigid that the vibrations transfer through the whole mass. And as you may have guessed, diamond conducts heat even better than graphite because each atom spreads that energy in 3 directions rather than 2. Graphite has another interesting response to heat. When it's heated to very high temperatures, temperatures around 3000 degrees Celsius and placed under extreme pressure, about 15 million kilopascals, the atoms rearrange themselves from a two-dimensional sheet network into a 3D network. Now, that's roughly the amount of pressure of 15 metric tons on 1 square centimeter, basically 5 elephants sitting on the heel of a high-heeled shoe. That tremendous heat provides energy for the breaking and reforming of bonds, which allows the atoms to reorganize themselves to relieve all of that pressure. And that, my friends, is how you can turn common graphite into diamonds. So no, you cannot do that at home. But just like with you and me, sometimes what seems like an excessive amount of pressure can end up forcing changes that stabilize things in the long run. The similarities, and especially the differences between diamonds and graphite, are an amazing display of the power of chemistry. Even though they're both made of the exact same material, a mere difference in the nature and arrangement of their chemical bonds completely changes their physical and chemical and electrical characteristics. Also, one is pretty and one is pencil lead. They explain why diamond can be used to cut through glass and drill through rock, while graphite is soft enough to write and lubricate with. And yes, diamonds are more valuable, but you could argue that graphite, with its easily erasable, mass-producible pencils, might have done more good for the world. The pencil is maybe mightier than the diamonds. This sand, and this glass, and this quartz are basically the same thing, just with the atoms arranged a little differently. The chemical name of this substance is silica, made up of silicon and oxygen in a 1:2 ratio. For that reason, we say that the chemical formula of silica is SiO2, even though it doesn't actually exist in separate individual molecules. Like graphite and diamond, the two forms of pure carbon, silicon and its oxides are network solids. And also like graphite and diamond, the different forms that they take are all about bonding differences. The form of the silica that makes sand is exactly the same as the form that comprises quartz. In fact, the silica in sand is basically just tiny bits of quartz. Silica's structure is based on a tetrahedral arrangement of a silicon atom bonded to 4 oxygen atoms. That's right, 4. Not 2. The trick is that each of the oxygen atoms can form 2 bonds, so they also bond to another silicon atom on the other side. So each silicon is bonded to 4 oxygens, while each oxygen is bonded to 2 silicons. Si2O4 simplifies to SiO2, and that's where we get the formula. As the molecule continues to build on itself, it can make various crystal structures depending on the orientation of the little tetrahedrons. These are different forms of quartz, clays, and other minerals. They can make 2-dimensional forms as sheets or 3-dimensional crystals, and each form has its own properties and behaviors. Ceramics and other clays get their strength from the 2-dimensional types. When the clay is wet, silica sheets move around freely in the clay, and as it dries they move closer to each other and bond together, forming a rigid framework. This resulting composite is extremely hard and heat resistant. Both of these properties make ceramics useful in tons of ways that you've probably been exploring since you were a toddler and got your first box of modeling clay. 3-dimensional silicates can take lots of shapes too, although not all of them are true crystals. Glass is an enormously important example of a 3-dimensional silica-based amorphous solid. It's worth mentioning here even though it's not a crystal, because its molecular structure is extremely similar to the structure of quartz, just not as orderly. The arrangement of silicon and oxygen atoms in quartz is very regular and rigid. The molecular structure of glass, on the other hand, looks like Mother Nature tried to build a quartz crystal while she was a little bit drunk. The atoms are attached in random numbers and shapes, creating a fragile structure with no definite order. This is why glass can be formed into almost infinite shapes when it's heated, while quartz keeps its characteristic crystal shape. Because it's an amorphous solid with bonds of varying strength, glass doesn't have an exact melting point. Instead, it softens as it's heated and becomes like honey-like, except extraordinarily hot and not sweet at all. Quartz doesn't do that. Its melting point is much higher, but it melts at an exact temperature and has no pliable in-betweeny state. Like all silica crystals, quartz, glass, and ceramics are electrical insulators because they have no free electrons to transfer charges over a distance. The atoms have 4 valence electrons and they form 4 bonds, so all of the electrons are perfectly well used. For this reason, these materials are used widely as insulators in electrical applications. Ceramics, for example, are used to hold live wires and power lines, and to make capacitors, which are basically layers of electrical conductors separated by layers of insulator. But all these silicon-based network solids I've talked about so far contain both silicon and oxygen atoms. Crystals made up of silicon are insulators too, in their pure state, but they can be made to transfer electricity by a process called doping. And no, we're not gonna make a Lance Armstrong joke. We might make an analogy though. It's like, much like a perfectly fit athlete injecting himself with all kinds of weird foreign stuff, silicon doping involves incorporating impurities into a crystal that mess up its electron balance. It can do that in one of two ways. If the impurity is an element with more electrons than silicon has, like phosphorus or arsenic, the resulting crystal will contain excess electrons. But if the impurity is an element with fewer electrons, like aluminum or boron, it leaves holes where electrons are missing from the normal structure. Doped silicon crystals are known as solid-state semiconductors. Those doped with elements that add electrons are called N-type or negative semiconductors because of the resulting charge from the additional electrons. With N-type semiconductors, the charge is carried by the excess electrons, and because there's no room for them to integrate into the structure, they move freely about the crystal. Similarly, crystals doped with elements that create an electron deficiency are called P-type or positive semiconductors because they have a more positive charge than pure silicon would have on its own. P-type semiconductors work a little differently. Because they have empty spaces available here and there, the electrons that are normally part of specific silicon atoms are able to jump around from one atom to another. Each jump fills a hole and creates a new one, allowing another electron to move in the same way. So if both N-type and P-type crystals are both electrical conductors, why do we call them semiconductors? Well, thank you for asking. The reason semiconductors are so valuable is that they have the amazing ability to conduct electricity freely under some conditions, but completely refuse to conduct it under other conditions. So yes, they are partial or semiconductors. So these properties become most useful when a P-type and N-type semiconductor are placed next to each other to form a diode. Because their charges are opposite, the free electrons in the N-type are attracted to the P-type and tend to migrate to its holes. And when an electrical field is applied to this arrangement so that the N-type is attached to the positive terminal, also called the anode, and the P-type is attached to the negative terminal, or cathode, all of the free electrons are pulled completely into the N-type. These free electrons are attracted away from the holes, not into them, so any further motion is blocked and no more current passes through the diode. This type of arrangement is called reverse bias. However, just by reversing the polarity of the electron flow, if you will, we can create a very different situation. If the N-type side is attached to the negative terminal and the P-type side attached to the positive terminal, then the electrons are pulled into the P-type, making this part an electrical conductor again. This process, called forward bias, is self-perpetuating and allows the current to readily flow through the diode. The fact that this conduction only works in one direction is extremely useful. You know AC and DC, right? Back in black for those about to rock. AC is alternating current, where the flow of electrons alternates in one direction to the other. In DC, or direct current, it's exactly what it sounds like. The electrons go directly where they're headed without backtracking. And simple arrangements of diodes can be used to convert AC to DC, like in this power supply for my laptop. P and N-type semiconductors can also be combined in sets of 3. These are called transistors, and they've completely revolutionized the field of electronics, also the entire world, since they were invented in 1947. One of the main functions of a transistor is to switch an electrical signal on and off. Basically, when it allows a current to flow in the forward bias direction, the switch is turned on. When the current drops below the minimum, the switch is turned off. This switching is the basis of binary code, ones and zeros representing the on and off states of the transistor. And that code is how we store and process information using computer chips, which are just collections of transistors working together. Such a tiny, simple device made mostly from one single element, and yet revolutionizing our entire world. That, my friends, is how Silicon Valley got its name and how network solids of silicon made this conversation we are having today possible. Thanks for taking advantage of all your tiny transistors today by watching this episode of Crash Course Chemistry. If you paid attention, you learned that sand and glass and ceramics and computer chips and much more are all really just different types of network solids that can be formed by silicon and its oxides. You learned the differences in their arrangements and bonding of atoms, and you learned how those differences result in wildly varying properties among the solids. You also learned what a solid-state semiconductor is, both P-type and N-type, and you learned how they can be combined to create diodes and transistors. Finally, you learned how transistors are combined to make computer chips, and how their switching mechanism tells computers what to do. I don't know about you, but it blows my mind. This episode was written by Edie Gonzalez and edited by Blake DiPastino. The chemistry consultant was Dr. Heiko Langner, and the script supervisor was Michael Aranda, who is also our sound designer. It was filmed, edited, and directed by Nicholas Jenkins, and our graphics team, as always, is Thought Cafe.